So next we come to the section about forces and torques on current loops. We mentioned this a little bit earlier, but now we'll more rigorously define how do we find the torque on a current loop and what the resulting motion will be. So let's think back to that example we did about a half loop. We wanted to find the force, the magnetic force, on the straight part of the wire and the curved part of the wire. What we found was that those two forces were equal and opposite, and we asked about the motion. We said overall it wouldn't translate, it wouldn't move up or down or left or right, it wouldn't go anywhere, but it could still move because the force on the top pointed into the page, the force on the bottom pointed out of the page, so that could actually let it rotate. So if it was rotating, it meant there was a torque. Let's take these ideas and now let's apply them more rigorously and let's find an expression for the torque on a current loop in a magnetic field. So let's think about a square loop, and let's think about a square loop as consisting of four straight segments. I suppose it could be rectangular, it doesn't have to be square. Let's assume there's a current that flows around counterclockwise. So there's a current I flowing in the loop. And we see that our magnetic field points towards the right. Let's find the force on each of those four segments of wire. And let's start with the top bit of wire. On the top bit, the current is to the left. The magnetic field is to the right. F equals IL cross B. Those two vectors are anti-parallel. And the force equals 0. Okay, now while we've got that idea in our head, let's do the force on the bottom part of the loop. The current goes to the right in the bottom part of the loop. So our current goes all the way around. Goes to the right in the bottom part of the loop. The magnetic field is to the right, so F equals IL cross B equals 0. Okay, there's the two easy bits done. What about the right-hand part of the loop? In the right-hand part of the loop, the current points up, that's your thumb. Your magnetic field points to the right, that's your index finger, and your magnetic force is your extended middle finger, that should be pointing into the page. So there's the direction of the force. The magnitude of the force is equal to the current times the length times B, because your L and your B are perpendicular. So really it's ILB times sine 90, but sine 90 is just 1. Okay, over on the left-hand side, your current is down, that's your thumb. Your magnetic field is to the right, that's your index finger. Your magnetic force, your middle finger should be pointing straight towards you. That magnetic force is out of the page. So if we look at our little square loop, what we see that overall, our net force is equal to 0. If our net force is equal to 0, our acceleration, which is force over mass, is also equal to 0. That tells us that there's no translation. This loop is not going to go across the room anywhere, but there's still motion because the right-hand side pushes down, the left-hand side pushes up. That means it's going to rotate. It'll spin around. If it rotates, that tells us that the net torque on that little loop is not 0. And in fact, the direction of the torque is going to point straight up. Or J hat direction, and we'll get to finding that direction. There's also a right-hand rule for finding torque. All the right-hand rules are the same. If you make a circle with your fingers that represent the rotation, so into the page on the right, out of the page on the left, you would see that your thumb points straight up. That's the direction of your torque vector as well. So you can do it with the math or you can use the right-hand rule. So we'd like to find this torque. Let's start to develop that. Let's imagine we look at this loop from the bottom. So let's get our eye in down this way. If we're looking at it from the bottom, then over on the left, the current is coming towards us. Over on the right, the current is going away from us. It's spinning around in a circle, so there's a pivot in the center, and our magnetic field still points towards the right. So on the left, our magnetic force is going to point up from our point of view. You can do that with your right hand rule, or you can just translate it from your diagram. And then on the left, your magnetic force will point down. The center is the point about which it will rotate. So the center is a pivot. And let's say that the distance from the center to either side is going to be our vector r. Because remember that torque is r across F. Okay, so let's apply that. Torque is equal to r across F. Sum of the torques on that little loop is the sum of each r crossed with each F. So r is your vector from your pivot, your point of rotation, to the point of application of the force. F is the applied force. For my force, I know it's the magnetic force, so I'm going to fill in the expression of my magnetic force. So I've got the sum of R crossed with IL cross B. I'm just going to move my current I to the front. So that leaves me with I times the sum of R cross L cross B. Now I'm just judiciously going to put in a couple of brackets around R cross L, because you can really put your brackets anywhere you wish. If you think about what is R cross L, that's the area vector of the loop. Okay, so that tells us that my net torque is current times area crossed with the magnetic field. Current times area, that might ring a bell. That's mu, the magnetic moment. And that is a vector. So our final result is that the net torque on any current carrying loop is mu, the magnetic moment vector, crossed with the external magnetic field it's sitting in. So that's how we find the torque on a current loop. So as a refresher, your magnetic dipole moment was current times area. This expression is for a single current loop. You find the direction of the magnetic moment by making a circle with your fingers to match the current. Your stuck-out thumb shows the direction of your magnetic moment vector. And if you had more than one loop, if you had n loops, the magnetic moment vector would be n times current times area. Okay, so the torque on a current carrying loop is mu cross B. You can always do your cross product to find the answer. Or you could use your right-hand rule to find direction, where your thumb is the first vector, that's mu. Your index finger is the second vector, that's B. And your extended middle finger is the third vector, that's the torque. So this goes with finding the magnitude, where the magnitude of torque is magnitude of mu times magnitude of B times the sine of the angle between mu and B. So you can always do the math, or you can do magnitude and direction with a right-hand rule.